Welcome to NASA Edge, an inside and outside look at all things NASA. We're here on the press site at NASA Kennedy Space Center in what is cloudy Florida. We have an historic launch today because we have the SpaceX Falcon 9 CRS-10 mission ready to go from Pad 39A, which is going to bring up 5,500 pounds of science experiments, research equipment, supplies bound for the International Space Station. And one of those cool instruments that is going up on the Dragon capsule is the SAGE 3 experiment, or the Stratospheric and Aerosols Gas Experiment. To kick things off, we have our special guest, Dave Bowles, who was with us yesterday. Dave is the director at NASA Langley Research Center in Hampton, Virginia. How you doing, Dave?
Doing great. Thanks for having me back.
So speaking about SAGE and Langley, how is SAGE and NASA Langley sort of related?
Well, it's a long history. Actually, this is called SAGE 3. So actually, the first SAGE went up in 1979. We had SAGE 2 in the mid-'80s, really looking at the ozone layer around the Earth and monitoring that, and has actually resulted in making some changes in what kind of chemicals we can use here on Earth. The ozone's starting to recover, and this is just another critical step in monitoring what's going on and having that continuity measurements. So really exciting.
You know, Langley started out as an aeronautics facility. We know that, but over the course of time, we did enter into the field of science, and we actually have a rich history of science.
Yes, good point. You know, obviously our heritage is in aeronautics, and then in the 60s, we were looking at, air density and things like that, really more focused on how it affects flight. But then we brought in some, really looking at the atmospheric chemistry to understand what's going on. And from then, we've really had a rich tradition. A lot of satellites we've launched, Earth-observing satellites. We have several on orbit now. Calypso, probably the longest one, has been up there for 10 years, collecting valuable data. So yeah, very rich part of our heritage.
And of course, 2017, it's a huge year for NASA Langley. It's our centennial.
Yes, it is. Yes. It's hard to believe. We broke ground on the first building there in Hampton in 1917 in July. So we have our official 100th centennial is July 2017. We have a lot of events coming up. Celebrate all across everything we've done: aeronautics, science, human exploration. The space program actually started at NASA Langley in the 50s with the original Project Mercury.
Well, I tell you what, Dave, Langley's had a rich 100 years. We're looking forward to the next 100 years at NASA Langley. And I'm sure that the technology in the next 100 years is just going to be phenomenal.
Hard to imagine. Yeah. I'm sure if in 1917 they couldn't imagine everything we're doing now. So.
Well, Dave, thank you so much for.
I feel the raindrops.
It's a perfect segue because we're going to go now to a segment that I did with Rich Ekman, who is the project scientist for SAGE and also the program manager for ACMAP. So let's check it out. So, Rich, you're the program manager for the Atmospheric Composition Modeling and Analysis Program at NASA headquarters. What's that program all about?
Yeah, the ACMAP program, as we call it, supports a wide range of investigations dealing with ozone and other trace gases in the atmosphere, as well as aerosols. Stratospheric ozone has been a major focus of the program for decades. Increasingly, though, tropospheric ozone, the ozone nearer to the ground, as well as aerosols in the atmosphere have increased in importance, particularly due to their impacts on human health.
So you're a program scientist for a very important Earth science mission called SAGE 3. How does SAGE 3 fit into ACMAP?
Almost perfectly, actually. SAGE 3 will continue a very long-term record of atmospheric ozone measurements, and instruments like SAGE have been key players in the data sources used by investigators working in my program.
So I assume SAGE 3 is a third in a series of SAGE satellites. So how has SAGE changed over time?
The first SAGE was launched in 1979, and then SAGE 2 just a few years later. Obviously, technology development has been dramatic over the past few decades. And the current iteration of SAGE instruments, the SAGE 3 series, of which there were 3 copies built in the late 1990s, have taken advantage of some of those technology developments. We're able to measure additional constituents in the atmosphere that have an impact on ozone chemistry. We're able to make measurements using other light sources. We've traditionally used the sun for a technique called solar occultation to measure the levels of ozone in the atmosphere. With SAGE 3, we're able to use the moon, a much less bright light source, but still a source that can be used. And so we're able to get additional geographical coverage of measurements of ozone as a result of these new measurement techniques.
Why the International Space Station for SAGE 3 and not a normal satellite that would orbit the Earth?
There are a couple reasons for that. The first is the orbit of the space station, which is a very good mid-latitude orbit. So with SAGE attached to the space station, we're able to view ozone from around 55 degrees north latitude to the same level in the southern hemisphere. So unlike a typical polar orbiting satellite, we have very good mid-latitude coverage. Another issue is cost. Attaching SAGE to the space station is a good deal less costly than a free flyer with a dedicated spacecraft bus and the various communications hardware that would be necessary.
Now, it seems to me that in that occultation process, that the orbit of the ISS would actually be very advantageous. Is that sort of the rationale?
Absolutely, because you can't move the Earth, you can't move the Sun. The only thing you can do is choose the orbit you're in. And so since we do occultation, where we look at the Sun and watch it set through the atmosphere, and that gives us our spectral signatures of all the absorbing gases and a vertical profile through the atmosphere, the orbit's key. And the SAGE 2 is in a 57-degree orbit, lasted 21 years, fabulous data set. And we've always wanted to put a SAGE 3 in a similar orbit. And the only game in town is Space Station. It's a fabulous platform. It's got lots of power, great communications, super team of people to work with. So we're really excited to be going there. Looking forward to arriving.
Yeah, and so, but it's interesting because the astronauts are not going to be the ones doing the work. The instrument's going to do all the work, and you guys down on the ground are going to be the ones looking at all the data that comes back.
Absolutely, they're busy enough doing the other things. So this was designed to be fully autonomous from the very outset, and we have a team of mission ops folks back at Langley that are going to be planning for the science events. We have some flexibility on what we can do. We're not only looking at the sun and the moon, but we have this ability to just look at scattered light, the blue sky that we have above us today. There's enough light there to make measurements of ozone and a few other gases. So they plan that, they send the command load up to the instrument, and it does its thing for the day.
Yeah, and you'll get that data every day and analyze it.
We get all the science data every day. We have to wait a little bit for the final MET data to come in, and then we go in and process it. So typically within a week we have the answers right there.
So exciting.
Yeah, I can't wait. It's been a very long time coming.
Well, it's interesting because you talked about the previous data set record from SAGE earlier. And so you're actually now going to start a whole new continuance of that record with even more data.
So one of the things about NASA is you rarely get to start something, but you're often allowed to carry the ball and continue on. So when I came here, started working with NASA in 1988, SAGE 1, SAGE 2 had already started flying. I started working on SAGE 2 data. I got to work the early design phase on SAGE 3, so I've been working on this project for 28 years or something.
Wow, that's awesome.
Yeah, it's a very long time.
That's awesome.
And, we're going to get this thing launched, start operating, and the next generation of scientists are there. They're working on SAGE 4. So you're just a piece in a continuum of activity, and you're just expected to do the best you can.
It's fantastic.
It's a fabulous job.
Now, just real quick before we go, because I'm curious about this. You solar occultation, I kind of understand, but the lunar. Explain how you're going to do that same process, but with the moon.
Yeah. So the thing about the moon is it's 1,000,000 times dimmer. So the first thing you have to do is figure out how are you going to have your instrument change something to give you a factor of 1,000,000, and it's very difficult. So we do that on a number of different pieces. We have a solar attenuator that takes out a factor of 200 or so. We can change the integration times on our detector. That gives us a factor of 10. But the key was in dealing with noisier data, but using lots of noisy data. It's kind of equivalent to what the folks that do Fourier transform spectroscopy do. They take 1,000,000 lousy points.
Oh yeah, those guys.
They take 1,000,000 lousy points, but it's great data. So with Lunar, we take 300 channels, And instead of 10 for ozone with solar, we have 300 of them, and just the statistics of that allows it to work. But once you see the moon, you can also go look at the blue sky because it's just about the same brightness. So we have this instrument now where the other ones prior SAGE were just solar occultation. This one does solar occultation, lunar occultation, limb scatter.
It's like you guys aren't leaving anything to chance. If there's some data out there, you're going to get it.
Well, you never have enough data.
Okay.
So Caitlin, you're the thermal lead for SAGE 3. For, projects or missions that have instruments inside the ISS, I don't believe they would really have to worry about thermal as much as you do.
Sure.
Why is that?
Well, because if they're inside the ISS, the environmental control of the station itself would take care of, it would put them in a benign environment where they don't need to worry too much about temperature extremes.
So when it comes to thermal testing for the SAGE 3, talk to us a little bit about, what you had to do.
The goal for the testing is to make sure that we can take all the components of our payload over a wide enough temperature range that we can be confident that they'll operate well in the extremes that they'll see in space, while also not taking them beyond the limits within which they can operate without anything going wrong.
Now, all the thermal testing for SAGE 3 was done here at Langley.
That's right.
Tell me the ranges of temperatures that SAGE 3 will experience in space.
The ranges we tested over were roughly, minus 40 degrees Fahrenheit up to about 160 degrees Fahrenheit. We don't expect they'll actually see that range of temperatures. The instrument actually is kept around room temperature with its heater, so that's around 65 degrees Fahrenheit.
Now SAGE 3 is made of several components. Did you test them all together in the thermal chamber, or was it separate?
Well, both. So initially, during the development of each component, we tested them in what we call subsystem testing. So those are shorter tests where we can focus specifically on what the performance is of a particular component. Those are on the order of a couple of weeks in the thermal vacuum chamber. And then once everything was integrated together into the payload, we put that into a larger chamber all together and ran a longer test, which was a little over a month.
When SAGE 3 arrives to the ISS, it has to be transferred from the capsule to its location on ISS. How will that be done, and what does temperature have to do with that process?
Sure, so that's done with the robotic arm on the space station. So the robotic arm will reach into the Dragon trunk, grasp our payload, pull it out, and then attach it to a platform that will translate us over to the location that we're going to end up operating at. And so for thermal, why that matters is there's portions of that translation time where we won't have any power to our survival heaters. The survival heaters are what keeps us warm enough when we're not powered operationally. And so it's important for us to determine ahead of time how long can we go without that survival power before we're in trouble.
So there aren't internal heaters that you can remotely turn on while it's being transferred. It has to be hooked up to operate the heaters.
Exactly,
okay,
yes.
okay.
So we have heaters internal, but we need power coming from somewhere external. So when we're in the Dragon trunk, we're getting power from the Dragon capsule. And then when we're on station, we're getting it from station.
I'm thinking that there were maybe like a set of 9-volt batteries on there that you can just hit a switch and it just...
Unfortunately, no.
Okay.
No. So they don't operate independently.
Okay, so during the operation of SAGE 3, you're going to be going from periods of maybe direct sunlight to when it's going to be in the shadows. How were those temperatures tested in the thermal chamber?
In the thermal vacuum chamber, we don't actually simulate the temperature profile around an orbit where the temperature is kind of going up and down. But what we do is we look at the maximum and minimum temperatures we expect to see, and we also look at the rate of change. And those things that we test are actually more extreme than what we expect we'll see on orbit. And so that gives us confidence that the payload's going to operate really well when it's up on space station.
And joining us now is the Mission Operations Manager, Brooke Thornton. How you doing, Brooke?
Pretty excited.
Aren't you?
Very excited.
How long have you been working on SAGE 3?
Almost 8 years now.
8 years.
Yes.
Right. Can you just kind of take us through, before we talk about what you do, is take us through that the motions of working on this instrument for 8 years, and you're finally going to see it launch.
Very emotional, very excited. I've been on this project since we started putting together the requirements to develop it, go through all the testing with an amazing group of engineers and scientists that we have, and now prepping for operations and getting ready to finally do my job.
Right.
So very excited.
Now, will you be still working with the program, making sure that the spacecraft, this instrument is healthy and that you're getting the proper data that the scientists need?
Yeah, so that's the main, my main job is to make sure that we're getting all the science data, all the health and status data down. The health and status obviously tells us how healthy the instrument's doing, making sure there's no issues. So the primary job is to make sure it's working properly. And then we're going to be working with the scientists to tweak the instrument, make sure we give them the best data that they can get.
Now, take us through it. You're a mission operations manager. Take us through any challenges because you have to work not only with the scientists, but I'm assuming you're working with the engineers as well, to trying to get them to work together. What are some of the challenges of being an operations manager?
I think that is kind of the biggest challenge is how do we optimize this instrument? Luckily, I've got a background in physics and engineering, so I can kind of do the geek speak if need be for the scientists.
Right.
And, those first 90 days is really when we're going to have the engineers with us to really tweak it and make sure that we're getting the best. After that, the engineers will just be around in case there's an anomaly.
Right. Now, do you have any plans maybe to move on to Sage 4 down the road, or?
At this point, no, they're well on their way on Sage 4, and so I would love to be involved if they need it, but right now just concentrating on Sage 3 because it's a minimum of 3-year mission and could go to 2024 with current ISS schedule.
Oh, so you'll stay as mission operations manager for the life of the mission?
Yep.
Wow, that's a huge part of your engineering career.
Yes,
8 years plus that's pretty big.
Yeah, that's a big that's a NASA career right there.
It is.
Joe, we understand the significance and importance of Sage 3 from a science standpoint. Tell us a little bit about the engineering challenges you faced in mounting the instruments on the ISS.
So one of the things about Sage that makes it unique, aside from the science, on the engineering side, is that we were dealing with a mix of legacy hardware that was originally built, in some cases, to fly on the International Space Station, and in other cases was part of the Sage series that was made to fly on several vehicles. And so integrating legacy hardware with its historical nature and some things that are out of date with the platform that's ISS, which has its own challenges, those two things combined created some issues that we had to overcome.
And what were the particular challenges to meet Sage's goals?
We have an instrument that really needs to be on a platform that's fairly stable. We also have an optical system. It's a spectrometer, moderate resolution spectrometer. So we have to deal with things like contamination. Both of those things could be a challenge on a platform as large and as varied in its use as the International Space Station. So we originally, back in the first concept, and even when we restarted, decided that we would need to monitor those two environments, both from a vibration perspective and from a contamination perspective, so that we would have information about the health of our instrument on the ISS.
What kind of vibration problems do you have?
Right.
I mean, aren't?
Yeah, so you can think of all up to this point, all of the legacy Sage instruments have flown on some version of a free-flying spacecraft, which you can imagine is much smaller, easier to control than a large structure like the International Space Station, where you've got different things rotating, solar arrays rotating, you've got visiting vehicles that tend to change the attitude of the space station. Those challenges aren't present on a free-flying spacecraft. So whenever we would get a vibration potentially out where we were at, the science team would want to know that. So we had to have a way to at least flag the data for that kind of challenge. And that's kind of where the concept for the disturbance monitoring package came from.
So that disturbance monitoring system is kind of a way to kind of filter out some of this extraneous data when things aren't quite as they should be?
It originally started out as a flag, right? So you would tell the science team once they got the raw data on the ground that, hey, you potentially had vibration exceed what your spec would be. However, when we moved along in the concept development, we found that the science team could actually use that data to correct for vibration. Even if it was in spec, it would make their measurement better.
Nice.
So that kind of drove us in a particular direction. Not that uncommon in engineering design to start off with an idea, and then when you actually get to deployment, it ends up helping you in ways you didn't even think of originally.
We're almost 2.5 minutes away.
Yes, sir.
Yeah, we're almost there. And
light the candle, right?
That's right. So what we're going to be doing here in the next few seconds, we're going to go to the launch commentary and listen to George Diller. He's going to provide a commentary. He's been doing this for
a long time.
30 some years. Can you imagine that?
Time.
I mean, he is the guy for launches.
Yeah, he's the
here.
icon for it.
He never gets old.
Nope.
Hey, when's the last time you saw a launch?
guess 2009 Ares 1X.
Oh, wow.
Yeah, it's been a while.
So you got to really be
Oh,
jazzed.
I'm pumped and excited.
And the cool thing about this launch, and people don't really think about this, that Pad 39A is historic because we launched Apollo,
awesome. Yes.
we launched Shuttle,
I know.
and now we're launching SpaceX.
I know, it's exciting.
Okay, let's do it. So we got we got the weather. You know, we've got Steve Gaddis, who's our resident expert for Edge. And George Diller's going to make the call in a few seconds. So what we're going to do now is that we're going to go to the launch commentary, and let's listen to George Diller for the final minute. You're watching NASA Edge.
Falcon 9's in startup. Dragon is in startup. Stage 1 and Stage 2, pressing for flight.
LD, verify, go for launch.
LD verifies, go for launch.
Preparing now to go into terminal count at T-minus 30 seconds.
T-minus 30. T-minus 20.
Falcon 9's configured for flight.
T-minus 15 seconds.
T-minus 10.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition and liftoff of the Falcon 9 to the space station on the first commercial launch from Kennedy Space Center's historic Pad 39A.
Pad operations on Pad Net A.
Copy, Wilco.
Stage 1 propulsion nominal.
Oh, this is great. Now, you haven't seen a launch since 2009. How was it, Steve?
It was awesome.
Very
Awesome.
exciting. And, you could hear the cheers and the
Oh,
crowd.
yeah.
Very enthusiastic. Obviously, we're happy for the Stage 3 team, happy for SpaceX and all the other missions that are associated with this
Right.
launch. But what a moment. Nothing like it. Well, we just want to thank everybody for joining us, all the support team at KSC TV and the folks at Marshall, Lee Erickson in particular, for coming in and make this happen, and just all the Stage 3 team,
Yep.
the folks in your office that have helped us along the way. It's just been a great effort. And I want to give a special shout out to the folks in Europe that were posting comments on our site. Good to have people from across the pond watching the show and supporting all that NASA does and that ESA
Right.
does and our other partners do.
Yeah. Good
So
partners.
thanks again, Steve, for being on the show.
Glad to be here.
Until next time, we're NASA Edge, an inside and outside look at all things NASA.